Welcome all to the week 3 session of Fundamentals of Food Process Engineering. Can you see my slide?
Yes, ma'am.
Okay, so we'll proceed with the syllabus of week 3, and if you guys have any doubts, you can either unmute yourself or post in your messages, and I will reply back to your question. So, question 1, half-life of a reaction that follows first order kinetics is 2 minutes. If the initial concentration is C naught, what will be the change in concentration after 5 minutes? So uh, what is known as the half-life of a reaction?
The time taken for a reactant to reduce to half of its initial concentration.
Yeah. So half-life of a reaction is the time that takes for the concentration to reduce by half of its initial concentration. So for a first order kinetics, what is the rate proportional to? You guys have any idea of how to solve this? How to go about solving this? I don't want the answer, just the procedure. Okay, so first order kinetics, in first order reaction, the rate that is dC by dt, rate of change of concentration of a reactant, is directly proportional to its concentration. So since the rate of change is directly proportional to the concentration, when we remove the proportionality sign, we have a constant known as the rate constant. Now in this case, since we're talking about half-life of a reaction, we're talking about decrease in concentration, which is why we have a minus sign here. So dC by dt is equal to minus K, which is rate constant, into concentration of the reactant. So if we integrate it, say from C naught, which is the initial concentration, to C, which is the concentration at any particular time t. So we integrate it from C naught to C, and the time we integrate from 0 to t, we get ln C by C naught is equal to minus K into t. So how do you find out half-life of reaction from this equation?
Substitute C is equal to C naught by 2.
Yeah. So when you substitute C equal to C naught by 2, you will get your half time to be 0.693 divided by K, where K is your rate constant. So now we already know that the half-life of the reaction is 2 minutes. So 0.693 divided by K is equal to 2, from where you can get K, which is the rate constant, as 0.346 minute inverse. Now, how do you go about this is that now that you have the rate constant, you substitute it back in the same equation. You have time already, you have the rate constant. So we substitute it back to find out what is the concentration. So we substitute back minus 0.346 into 5 minutes, and we take the anti-log of this. We get C by C naught as 0.1773. This is the ratio of the final concentration by initial concentration. But what is asked is the change in the concentration at time t, that is 5 minutes. So percentage change is initial concentration minus final concentration by initial concentration into 100. So that you can calculate by, this is the same as 1 minus the ratio into 100. So when you substitute C by C naught into this equation, you will get 1 minus 0.1773 into 100, which is 82.3%. So the correct answer to this question is option C. Any doubt? Okay. Moving on to the next question. If I am going fast, please let me know. So question 2. The food product is cooked at 121 degrees Celsius for 12 minutes. The vitamin loss in cooking process follows the first order kinetics, and D121, that is D value for vitamin destruction, is 200 minutes. So what is the percentage vitamin loss during cooking? So what is D121 here? What does it mean? So D121, any D as such is known as the D value or the decimal reduction time. So time taken to reduce the concentration by tenfold. So half-life is time taken to reduce the concentration by half, and this decimal value or D value is the time taken to reduce the concentration by tenfold. So for 121 degrees, the D value is given as 200 minutes. So since it follows the first order kinetics, we'll have the same equation, ln of C by C naught equal to minus KT. So how do you find out the D from this equation? So since I told that the concentration reduces by tenfold, so C becomes C naught by 10. So this becomes ln 1 by 10, which is equal to minus K into D. So D is the time at which C becomes C naught by 10. So if you find the value of ln 1 by 10, it will come out to be 2.303 divided by K. So when you have D, you can always find the rate constant. Here it is given that D121, that is the D value at 121 degrees Celsius, is 200 minutes. So from this you can calculate the rate constant. So what is the rate constant in this case?
Point 0.0115.
Yeah, so K is coming out to be 0.0115 minute inverse. So from there you can calculate again the percentage change in concentration. So ln C by C naught is equal to minus K into T. So K you just found out to be minus 0.0115, and the time taken for the process is given as 12 minutes. So total it is coming out to be minus 0.1381. That is the ln C by C naught. From this again you can calculate C by C naught as 0.871. The percentage change is C naught by C divided by C naught into 100. So again 1 minus the ratio into 100 will give you percentage change. So 1 minus 0.871, which you derive from this step, into 100 will give you 12.9%. The correct answer to this question is option B. Clear as of now?
Yes, ma'am.
So anytime they ask for a change in concentration, try to figure out either the rate constant or the time according to whatever is given in the question. From there we can find out the ratio and then the percentage change. So how you relate decimal reduction time with the original equation, that is the number of microorganisms, is that log n naught by n is equal to T by D. Here you can see a difference. It is not natural logarithm, it is log to the base 10. So you need to be very careful as to what you are using here. You can substitute K as 1 by D only when you are using log. You cannot substitute K as 1 by D if you are using a natural logarithm. So that you have to make sure that you are using it correctly. So this is the relationship between the number of microorganisms and the decimal reduction value. Moving on to question 3. The D values of the microorganism at 121.1 degrees Celsius and 135 degrees Celsius are 1.25 minutes and 0.12 minutes respectively. Calculate the total processing time for 99.999% of reduction of the microorganisms at 130 degrees Celsius. So any idea how to proceed with this? So in this case, although you can find out n and n naught from this 99.999% reduction, you cannot use the same value of K or time for different temperatures, because higher the temperature, lesser is the time required to sterilize a product. So K and T will depend upon the temperature that you are using. So we cannot use our previous process. We'll have to use a different technique. So in this case, given T1 is 135 degrees Celsius and D1 at that particular temperature is 0.12 minutes. T2 is 121 degrees Celsius and D2 is 1.25 minutes. So as you can see here, if you reduce the temperature, D value is increasing. This is because at a lower temperature, it takes more time for the organisms to be reduced by 1/10 of the initial value. So as the temperature decreases, you will generally see that the D value increases. So what we need to find is temperature at 130 degrees Celsius. What is the total processing time? So what is given to us is that we are reducing the amount of microorganisms by 99.999%, which means that only 0.0001% is remaining in the product. So n is equal to 1 minus the entire probability into n naught. So this will be your number of microorganisms that are surviving. So n and n naught are always viable cells. They are not dead cells. That you need to make sure. So n is the number of viable cells at time t. N naught is the number of viable cells at time t equal to 0. So we have n, we have all the temperatures. The procedure which we are going to use is using the Z value. Do you guys know what a Z value is? You can post it in the message also, chat also, if you guys know. So the Z value is the temperature difference that it takes to reduce the D by 1/10. So D is the time that it takes to reduce the number of cells by 1/10, whereas Z value is the temperature that it takes to reduce the D by 1/10. So if you plot a graph with D in the log scale, not log D, D in log scale versus temperature, you will get a straight line. So let's say this is somewhere around 10 power 3 and this is somewhere around 10 power 4. So the temperature that it takes to reduce from 10 power 4 to 10 power 3 is the Z value. So the temperature difference that it takes to reduce by 1 log is called the Z value. So from this graph, you can find out that Z is equal to delta T divided by log of D1 minus log of D2. So if you rearrange this equation, that is you take the log, you take the anti-log. So you will have D1 by D2 equal to 10 power T2 minus T1 by Z, where D is the decimal reduction value and T is the temperature, Z is the Z value. Is this clear? Okay, so if you substitute the values in this particular equation, what is the Z value that you are getting? Is anybody calculating the Z value? So if you substitute, okay, let's find out the Z. So if you substitute D1 as 1.25, okay, the other way around. So D1 is 1.25, D2 as 0.12, you'll accordingly substitute it the other way around. So what is the Z value that you're getting? Yeah, you have to take log to the base 10 on both sides, so that you will get, here it will be log d1 by d2 equal to t2 minus t1 by z. Here log to the base 10 and 10 will get cancelled. So you will have 135 minus 121.1 divided by z on the RHS, and your LHS will have log 1.25 divided by 0.12. So this is log to the base 10. So Z value comes out pretty close. 13.65 is what the Z value comes out. So again, now since we know for two different temperatures, we are calculating for the third temperature. So again, if you substitute any one of the temperature and its D1 value, you can calculate the D2 value at 130 degrees Celsius. So if you go about calculating D2 at 130 degrees Celsius, you are getting D2 equal to 0.278 minutes. So we get D2 equal to 0.278 minutes. But what is asked is the processing time, not the decimal reduction value. Can you please mute your mic? So we need to find the processing time and not the decimal reduction time. So how you find the processing time is that log n naught by n is equal to f by d. So only when you have a log can you use the term d, and instead of time we are using f because we are talking about the entire processing time here. So the entire, when you are talking about the entire processing time, you can substitute t as f. So k will become 1 by d and time will become f. So log n naught by n will be equal to f by d, where f is also called as the thermal death time or the total time required to accomplish a stated reduction microbial population. Let's say you want to reduce the population by 99.99%. So what is the time required to reduce it by 99.99% is called the thermal death time, or F here. It is also called as the processing time. So when you substitute log n naught by n and you also have the d value, what is the value of F that you are getting? So n will be 1 minus 0.9999 of n naught as per our previous slide. We are reducing it by 99.999%. So n naught and n naught will be cancelled. So when you substitute n naught and n, so n will be 10 power minus 5 of n naught. So n naught gets cancelled, and log of 1 by 10 power minus 5 is 5. So 5 equal to f by 0.278. 0.278 came from the d value that we just figured out. So f by d, and f comes out to be 1.39 minutes. So this is the processing time, that is it takes 1.39 minutes at 130 degrees Celsius for the entire process to be completed such that 99.999% of your bacteria gets killed. So the correct answer to this question is option A. Moving on to question 4. A food product is sterilized in a retort. Retort is something like an autoclave where you sterilize by extremely hot water or steam at very high temperatures. So a food product is sterilized in a retort. The time and the temperature at the center of the can is given below, which is given here. Calculate the F naught if Z value is 10 degrees Celsius. So we know what F is. F is the processing time. What is F naught here? Any idea on what F naught is? So F naught is the thermal death time at a reference point. The moment you see a naught here, except for N naught, for F naught, D naught, everything refers to that particular parameter at the reference temperature, which is 121 degrees Celsius or 250 degree Fahrenheit. This is pretty much constant. In case of an autoclave or something, or a retort, you will have a reference temperature of 121 degrees Celsius or 250 degree Fahrenheit. This is like a default value. So you can actually find out F naught using a parameter known as lethality factor or lethal rate. So what lethality factor is that? Time taken at 121 degrees Celsius to obtain a sterilization value equivalent to 1 minute at some other temperature T. So let's say at somewhere around 100 degrees Celsius, you are able to obtain from 10 power 5 to 10 power 4 cells in 1 minute. So how much time does it take at 121 degrees Celsius to reduce the same amount, that is from 10 power 5 to 10 power 4. The same lethality rate or the same amount of killing should happen at 121 degrees Celsius, same as what happens in 1 minute at some other temperature. Is the lethality factor concept clear? Are you able to understand what lethality factor means?
Yes, ma'am.
Okay, so we used a sentence known as sterilization value. So sterilization value is nothing but the log reduction of my microorganisms. Let's say log initial concentration of the bacteria divided by final number of initial number of bacterial cells divided by final number of bacterial cells. And this, as we found in the previous slide, is equal to F by D, where F is the process time and D is the decimal reduction value. So the time taken at 121 degrees Celsius to obtain certain microbial reduction as same as that obtained in another temperature for 1 minute. So how we connect lethality factor and F naught is that first we have to figure out how to calculate lethality factor. Lethality factor can be expressed by L, which is equal to 10 power T minus T naught by Z. So Z, as we know from the previous slide, Z is the Z value. That is the time taken to reduce D by 1/10 of its value. And T naught is your reference temperature, that is 121 degrees Celsius. So you can find out lethality at any particular temperature if you know the Z value. So here Z value is already given as 10 degrees Celsius. But we have multiple temperatures given in the data. So for each data point, we will figure out what the lethality factor is. So once we find out what a lethality factor is, we need to plot it by time. So this is just a representative graph. This is not the solution for this particular problem. So as you can see, as time increases, your lethal rate first increases, then remains constant and decreases. This is because if you have a food product and you're trying to heat it up to say 121 degrees Celsius, it does not immediately reach the temperature. It takes a little time to reach 121 degrees Celsius. So as it gets heated up, your lethal rate, that is the amount of killing or the rate at which your microorganisms are killed, are also slowly increasing. The moment it holds at 121 degrees Celsius, your lethal rate will be pretty much constant. And when you're trying to cool down the product also, you'll see that your lethal rate starts falling because now the temperature is dropping. So as you can see, your lethal rate will actually change with respect to time. So if you plot the lethal rate of any process versus time and you calculate the area under the curve, the area under the curve will give F naught. So this is the relationship between F naught and lethal rate. So F naught is L into delta T, summation of L into delta T, or you can do it by integration or by a graphical method as well, where you find out the area under the curve. So as given by the previous equation, lethality rate can be calculated by 10 raised to T minus T naught divided by Z. So T naught is 121 degrees Celsius, Z value is given as 10. So for different temperatures, you will have different lethality rate. For the first row in the data, you have 25 is your time interval. Sorry, 25 minutes is your time interval, and 10 raised to 70 degrees Celsius is your temperature at that particular point, minus 121 divided by 10. The second data point is again 25 seconds interval into 10 power 95 degrees Celsius, which is the temperature at that particular time, minus 121 divided by 10, which is the Z value. Plus your third data point has a time interval of 20 seconds. So 20 into 10 power 105 minus 121 divided by 10. So for each particular data point, you will calculate the lethality rate and multiply it with the time interval. So when you add everything up, this will basically give you the area under the curve or the F naught value. So the F naught value comes out to be 0.565 minutes. Is this clear? Because this is also a part of your assignment 3. You will have similar questions in assignment 3. Any doubt as to how to calculate F naught? Okay. So here in this question, you already have the time interval. So what will happen if you have just the time and the temperature? How do you calculate when you have only the time and the temperature instead of the time interval? So when you have only the time and the temperatures, you will find the lethality as usual for every single time. Like say for L4, that is at 1, 2, 3, that 15 minutes, your lethality will be 10 power 163, because we're talking about so for 5 seconds you will actually consider the next value of temperature. So for 5 you will consider 140 degrees Celsius, for 10 again you will consider 140 degrees Celsius, and for 15 you will consider 163 degrees Celsius. So you're talking about time intervals here. So you will have to calculate accordingly. Say for L4, that is at 15 minutes, your temperature will be 163. So 10 power 163 minus 250. So in Fahrenheit, your reference temperature is 250 and not 121. So 163 minus 250 divided by Z. Can you mute your mic, please? So you'll calculate L4. Similarly, you'll calculate for every single temperature point. So after you calculate L, in this particular problem, you'll see that all the time points are equally spaced. That is, there is 5-minute interval gap. So since delta T is constant, you can have F naught equal to delta T into summation of L. So you will calculate lethality rate at every single time point. You will sum all the lethality rate up, that will give you sigma L, and then into delta T, which is 5 minutes here. That is how you calculate F naught when you don't have time intervals. Any question? Okay. So moving on to the next question. So in a thermal processing of food, the initial microbial population of 10 power 4 organisms per container is subjected to heating at 140 degrees Celsius for 60 seconds. So estimate the spoilage probability at the end of the process. The decimal reduction time for the organism at 140 degrees Celsius is zero point 0.1 minutes. So any idea on how to go forward with finding out the spoilage probability? Do you see anything different from what we saw in the previous question?
Spoilage probability.
Yeah, that is one thing. At each question, we'll be learning one single concept. But here, unique thing is 10 power 4 organisms per container. All this while we're talking about the total number of organisms present in the batch. This is the first time we're talking about per container. So this means that now we're talking about different containers, but all these containers together will form one single batch. So there'll be multiple containers and all those containers will be one single batch. So N naught here will actually be 10 power 4 organisms per container. You cannot leave this per container concept out. So 10 power 4 organisms per container. Temperature given is 140 degrees Celsius. Time 60 seconds or 1 minute. And the decimal reduction time given is 0.1 minutes. So how you go about finding spoilage probability is that first we need to understand why we are dealing with per container here. So generally our previously our equation was log n naught by n is equal to f by d. That is f is equal to d log n naught by n. But now you have a certain value called r multiplied along with n naught. So since we're dealing with per container, you have to find out the total number of organisms present. So you'll have to multiply it with the total number of containers present with you. So r stands for the number of containers. So we assume that only one, whenever you're finding out spoilage probability, there is one assumption that you have to make. So we assume that only one organism survives in the entire batch. And when I mean batch, it means all the containers together, there is only one single organism that is surviving. So R into N will be equal to 1. It is not one organism per container, it is totally one organism that is surviving. So R into N is equal to 1. And here 1 by R is actually the chance of spoilage or spoilage probability that you have to calculate. So now, how do you go about this? So if R into N becomes 1, what is your equation? So when R into N, that is your denominator, becomes 1, your equation will become F equal to D log R into N naught, where N naught is number of organisms per container, R is the total number of containers. So this will give you total number of organisms. So we can just substitute the values 1 minute equal to 0.1 minutes log R into 10 power 4. And 1 by R is what we need to figure out. So what is the value of 1 by R that you are getting? Is anybody calculating? So 1 by r value, when you simplify this equation and calculate, you will get 1 by r as 10 power 4 divided by 10 power 1 by 0.1. Okay, so this comes out to be 1 by 10 power 6, which means that there are total 10 power 6 scans, that is r is equal to 10 power 6, which means there are total 10 power 6 scans, and one organism is surviving in one of the cans, that is leading to this spoilage probability. So the chances of spoilage is one organism, that is one can, in 10 power 6 cans. So the answer to this question is option C. Yeah, so 10 power minus 6 will be the probability, but since all uh, the options are given in some kind of x number of cans, you will have to interpret this in such a way that it means that one organism present in one can spoils up among the 10 power 6 cans. 10 power 6 cans. So yeah, chances of spoilage will be 1 in 10 power 6 cans, and the answer to this option is answer to this question is option C. Moving on to question 6. The Z value of a microorganism is 12.8 degrees Celsius. Find the equivalent process time. Here process time means the F value as we discussed earlier. Find the equivalent process time at 115 degrees Celsius, which will give the same lethality as the thermal process calculated at 121 degrees Celsius for 8 minutes. Any clue how to do this? This is also one of your question in assignment 3. So you have the Z value given. You need to find out at 115 degrees Celsius, which is your say T2, and T1 or your T0 here is 121 degrees Celsius, and the time required is 8 minutes. So any clue how to go about it? So given here, since we're dealing with 121 degrees Celsius, which is the reference temperature, we'll name this as T0. And since we are given the process time here, 8 minutes, this will be F0. So anything that happens at the reference temperature will have a subscript of naught here. So T0 is 121 degrees Celsius, F0 is 8 minutes, which is your process time. What we need to find out is the process time at 115 degrees Celsius. So what is expected is that when you reduce the temperature, the process time will automatically increase. So how you figure that out is there's a relation between your process time and your decimal reduction value and your rate constants. All these are three different things. This is your process time. Decimal reduction value is the time required to reduce the concentration by 1/10, and rate constant is what you get from your first order reaction. So this is equal to 10 power T1 minus T2 by Z. We already calculated d2 by d1 equal to 10 power T1 minus T2 by Z. We also have other relations in terms of F and K, that is also equal to 10 power T1 minus T2 by Z. This is because you have all these relations because F is directly proportional to D and inversely proportional to K, which means that the longer it takes to reduce the organism by tenfold, that is, the higher the D value, longer is the process time to achieve the desired sterility. The more longer it takes to reduce by 1/10, the more higher your process time is going to be, which means your bacteria is actually resistant to that much amount of heat. So the higher the D value, higher the resistance to sterilization. So the longer the time. But on the other way around, if your reaction rate, that is your microbial death kinetic rate, is extremely high, then it means that your process will be over in a much more shorter time. So your F will be inversely proportional to K. Is this clear? Any doubts? Okay. So here, for to apply in this formula, let us take your T1 as T0 and F1 as F0. So F2 by F0 will be 10 T naught minus T2 by Z. So if you substitute the values, it will be F2 by 8 minutes for 121 degrees Celsius, 10 power T2, that is 121 degrees Celsius, minus 115 divided by 12.8, which is your Z value given. So from this, you can calculate 23.5 minutes to be your process time at that. So what I meant in the previous slide is that D value, higher the D value, higher is the resistance of the bacteria to sterilization. It does not get killed that easily. So if it does not get killed that easily, then your time taken to actually kill it will also increase. So higher the D value, higher the F. D value is the time required to reduce the concentration by tenfold. So if this is higher, if the time required is higher, then your total process time will also be higher. Whereas when we are talking about your reaction rate, let's say your microbial death kinetics reaction rate is extremely fast, which means that your number of cells are rapidly decreasing. This means that your bacteria is now sensitive to heat. So the more sensitive it is to heat, higher will be the rate of your reaction and lower will be the time required to kill the bacteria. So higher the rate, lower the time required. Higher the resistance, higher the time required. It's just that simple concept. So this relation you can use for calculating F2. So F2 is 23.5 minutes and the answer to this question is option C. So this is pretty straightforward. The number of microbial count doubles in 6 hours. So how many times does the microorganism grow in 10 hours? So how will you proceed with this? So what is N here? That is the number of microbial cells in 6 hours. What is the N here? So we're talking about microbial cells doubling. So your N will be equal to twice the amount of your initial condition. So we're talking about doubling the microbial count. So it will be 2 into N naught, not 6 into N naught. Yeah. So generally we assume that microbial growth and death kinetics are first order reactions. But in the case of death kinetics, you're talking about a decrease in concentration. So you'll have a negative sign there. But when you're talking about growth, you'll have a positive sign there. That is ln n naught n by n naught equal to kt. Had this been a death kinetics, you'll have minus kt here. So you'll substitute n as 2n naught. And what is the value of k that you're getting? You have time here as 6 hours and n is equal to 2 into n naught. So what is the k? So k value is coming to be 0.116 R inverse. That is not the answer that I'm getting. Ln 2 is 0.693 and you will get 0.693 divided by 6 if I'm correct. You have to make sure that you're talking about natural logarithm here, not the log to the bar 10, log to the base 10. So your k value should come around somewhere 0.116 R inverse. So when again you can substitute the k back in this equation and you already have time t equal to 10 hours, then you can calculate the n by n naught from that. So substituting the k value back, ln n by n naught is 0.115 into 10 hours. So n by n naught, if you take an anti-log of this, you will get somewhere around 3.16. So now your current bacteria is about 3.16 times higher in amount when compared to the initial concentration. So it is growth is around 3.16 times. So the answer to this question is option D. Moving on to the next question. This is more of a fill in the blanks. The thermal death kinetics following the first order reaction is given by one of the relationship where theta is the time in this equation. So which do you think is the correct answer to this question? Where n naught is initial microbial count, n is the microbial count at time t equal to theta, k is your reaction constant and theta is the time. So which one of these is the correct relationship? Any guesses? Any answers? So why don't we solve this first? The answer is not option D. We'll solve this first. So dn by dt, since it's a first order reaction, dn by dt is directly proportional to n. So dn by dt is minus kn. Since we're talking about death kinetics, there will be a negative sign here. So when you integrate it, you're going from n naught to n and you're going from 0 to theta. So when you integrate this, you'll have log n from n naught to n and k into t. So this is what we'll get, natural logarithm n by n naught equal to minus k theta. Then if you take an anti-log, it will be, since there's a negative sign, you will flip this, n naught by n is equal to e power k theta. So your answer is A. The reason why we are not talking about log here, because it's a natural logarithm that we are taking. We need to be very careful as to what you are taking, if it is log or ln. The correct is actually ln only. You cannot put 2.303 log n by n naught, take 2.303 here and put that as a constant. We are not talking, this constant is different from a normal integration constant. K is the reaction rate. You cannot put k by 2.303 and state that as your reaction rate. Reaction rate will only be k. If you want to express in terms of log, it will be 2.303 log n by n naught equal to minus k theta. You cannot put 2.303 in the RHS and then consider that as some other constant. That is now not how we define first order reaction in case of thermal death kinetics. So n naught by n is e power k theta, or else this will be valid but only when there is a 2.303 here. So the answer to this question is option A. Moving on to the next question. The thermal death time plot is one of these. It's either log D versus log T, or n naught by n versus time, log D versus time, and semi-log plot of heating time of inactivation versus temperature. Have you heard of the thermal death plot anytime? So what's the thermal death plot? The thermal death curve provides information about the time required to kill a particular organism at variety of different temperatures. So when you plot a thermal death time plot, you will have temperature in the x-axis and your heating time required, that is your process time, in the log, semi-log scale. So this will be in the log scale. This won't be log of time. This will be time in the log scale. There's a difference. So this will be in the log scale, that is, and this will be in the linear scale, which is why it is known as the semi-log plot. Only one of the axis is in log. So your y-axis will have the heating time. Your x-axis will have the temperature. So when you, so this particular curve that you get is called the thermal death time plot, and z value is what you calculate from here as well. That is the time required to reduce the d value by tenfold. So the answer to this question is option D. Moving on to the last question. Calculate the sterilization value of a microorganism at 130 degrees Celsius if the thermal processing at that temperature results in 99.99% elimination of microorganisms. So, do you remember what the sterilization value is? We discussed it somewhere around probably question 3. So, sterilization value S is equal to log n naught by n. So, here it is log to the base 10. So, you need to make sure that this you understand well. So, log n naught by n, and it is already given that 99.99% of the microorganisms are eliminated. So, your n, that is number of viable cells left, is 1 minus 0.999 into n naught. This is the number of viable cells after your thermal processing is complete. So n will be equal to 10 power minus 4 into n naught. So when you substitute back in this equation, you will get S equal to log n naught by 10 power minus 4 into n naught. So n naught will get cancelled, and log of 10 power 4 is 4. So your sterilization value is 4. So another name for the sterilization value is called log reduction cycle. So when S is equal to 4, it means there are 4 log reduction cycles. That is, it is going from let's say 1 to 10 power minus 4. That is 4 times 4 log times it is reducing the concentration. So your S value is also known as the log reduction cycle. So the answer to this question is option A. So you guys have any doubt in any of the questions so far? These are all, each question will have a different concept, and each of these concepts will be used in assignment 3. And pretty much all of these questions are taken from the concept from the last 2 lectures of the week. That is probably lecture 14 and 15 is from where we have taken majority of these questions. So the theory to all these questions will be there in those 2 lectures, and many of these concepts, almost 90% of these concepts, will be used in assignment 3 and will be useful for solving those as well. Any questions?